All right, so in this video, we're going to do the RMS value of a square wave. I also wanted to write an alternative version of this formula, like I said. We can convert this formula into a little bit more useful. Not that this one's not useful, it's plenty useful, but a little bit more convenient way to do the math. So instead of treating everything in terms of time, we can treat everything in terms of angles because these signals are periodic. Instead of treating one full period as time t, we can just treat one full period as 2 pi radians. And so instead of integrating 0 to t, we can integrate 0 to 2 pi. And the only difference is that we just need to treat our signal as a function of omega times t, d omega t, rather than d dt and a function of t. Okay, so this is a very unique way to do the math. It's very convenient though, and I think you're gonna like it. It makes the integral work out quite a bit better than what I did previously. So if you want some practice, you can go ahead and try and rederive the sine wave. You should get the exact same result, but using this formula, which is just a change of variables from the original. Okay, so for a square wave, for this particular one, I'm going to say that it's centered around 0 with a 50% duty cycle. So let's go ahead and draw that. It'll look something like this. Did I draw it in black over here? Yeah, I did. So let's do it again. So it'd be something like this. Just like this. Okay. And so this is going to be, we'll just call it VP and minus VP. Expected time. Sorry, we'll do omega t because I want to use that other formula. And so we're going to call this one pi, and this one will be 2 pi. All right. And so this will be my Vs of t. Sorry, Vs of omega t. I keep making that mistake now. If I do this, I can say that my Vs of omega t is equal to Vp, basically from 0 is less than omega t is less than pi, and minus Vp from pi to 2 pi, right? Just like that. Okay, so if I were going to go ahead and try and take the RMS value of this signal, I would write that Vs RMS is going to be equal to the square root of 1 over 2 pi times the integral from 0 to 2 pi, except I need to split this integral because it's got two different parts. So I'll go 0 to pi for Vp squared d omega t, and then I'm going to go pi to 2 pi of minus Vp squared d omega t, which I hope you see that minus Vp squared is just going to become Vp squared, so I can really just integrate this from 0 to 2 pi right off the bat. I just wanted to show that. So that can go, actually let me just write it here. The square root of 1 over 2 pi times the integral from 0 to 2 pi d omega t, and I'm going to pull the Vp squared out, so I'll just put that here. And so if we take that integral, we're going to get, I'm running out of space here. Let's move this up. So let's say Vs RMS is equal to square root of Vp squared over 2 pi. And I'm going to have to take the integral of omega t from 2 pi to 0. I'm going to get 2 pi minus 0. My 2 pi's are going to cancel. I get the square root of Vp, so I get that the RMS value of this waveform is just Vp. So we got that another signal that we can see clearly has a average value of 0, right? Its average value is 0, but its RMS value is Vp, which is up here. Okay, so that's an interesting result, but that is the case for a square wave that is oscillating around 0. Okay, so we've got this square wave oscillating around 0. We got the sine wave oscillating around 0. In the next video, we're going to do a square wave that does not oscillate around 0. Rather, it oscillates around some DC value. So it'll, instead of being down here, oscillating around 0, we're going to move it up, and it's going to oscillate around some DC value, and we're going to see what that does to change our RMS value. Okay, so I'm going to go ahead and end this video right here.